Welcome to a lesson with Dr. Powell. Let's take a look at how we can prove for a planar graph that is simple, so at most one edge between um, uh, two vertices, and it's undirected. And there's the number of edges is bigger than one. That for such a graph, that you don't need more than 6 colors to color the vertices such that no two adjacent vertices will have the same color. You wouldn't want red and red together. So, but 6 is all we need. In fact, actually, it's not the optimum. You can even do better, but we're going to prove actually that 6 is enough colors at least. You can there's the proof that 4 colors is enough is challenging. But right now we're going to focus on the case. We're just going to focus to show that 6 is enough. Okay. So, and we're going to use some of the results that we mentioned in the in other videos before this one. Okay. So in order to do this, we're going to do an induction argument, and we're going to use the fact that there's always a vertex in here lurking somewhere such that its degree, or the number of edges that it actually touches, is at most 5. So there's always that. So our induction argument is going to be to remove this to get to a lower case. So we're going to induct on the number of vertices in the graph. So let's suppose we have a graph G, all right? And let's suppose that we let AN be the statement that that we can use, that 6 colors are enough. So 6 is enough for N vertices. And let's suppose that we know that, well, in the base case, when N is, the base case to follow this, I mean, N has to be at least like 3. And that's pretty clear, 3 vertices, that should have enough. So the base case when N is equal to 3, or at least, so the number of vertices is 3, is pretty clear, because I mean, you could just use 3 colors, you're good. So the base case is satisfied, so we really need to show that AN somehow implies AN plus 1. So let's start here and look at this, and look at a graph that has N plus 1 things in it. So let's suppose that G has N plus 1 vertices. Now let's take a look at that graph, and let's remove the vertex that's lurking in there, that's connected to, that has at most 5 connections. So if we remove that, you actually now have a graph with N vertices. Now a few things can happen. Maybe when you remove that particular vertex and all the edges that are connected to it, you may actually disconnect your graph. So you'll have 2 separate connected components. I mean, that's possible. But no matter what you do, your graph will still be planar, and the 2 connected points, if you had them, would still be planar. The number of vertices in each of them would be less. The connected components would still be simple, so that's good. Still undirected. What would happen if the number of edges of either one of these components would be not satisfy that? Well, trivially, 6 colors would be enough in each piece, or that where this condition fails. So no matter which way we look at it, we can just kind of assume without loss of generality that these conditions apply to the graph when we take this away, which means when we take this away, we're in the right hypotheses have been satisfied for saying 6 is enough. So 6 colors is enough if we remove this point. Now, if we put the point back in, let's think. There's at most 5 different connections. So there's at most 5 different colors it's connected to. So what color now should we use? We'll just use the 6th one. And hey, that means that 6 colors was enough for our graph that had n plus 1 vertices. Therefore, we have shown this is true based upon this assumption. Where did we use this? We used this when we said, hey, we're using a graph with n vertices or even less than n vertices. I mean, we could have said in particular any subgraph of this. If we assume that 6 is enough for this, then 6 is enough for any subgraph of this, which means any graph with vertices less than n. So really that's where we use the assumption. The inductive hypothesis assumption was here in this case when we removed this, and then we knew that that was enough because the theorem applied in that case. And that was the assumption that it did apply when we had less vertices. Now, when we have more vertices, having less vertices implies it. And that's the proof. Thanks for watching.